Hello everyone, I welcome you all to this second lecture of states of matter. So in the previous class, we have seen about the three states of matter, which are the solid state, liquid state, and gaseous state. We have defined what these states are. Then, in addition, we have also seen the triple point. So triple point is a temperature at which all three phases exist simultaneously. Then we have studied about the different types of molecular intermolecular forces, and out of the four forces, which are dispersion forces, dipole-dipole forces, dipole-induced dipole forces, and hydrogen bonding. We have in detail covered the dispersion or London forces, right? So in this class, we are going to go further and study about all the remaining three forces, right? Let us write this down. So this is lecture 3, lecture 2, states of matter. The first topic which we are going to see is dipole-dipole forces. These are also called as Keeson forces, right? So dipole or Keeson forces, right? So these types of forces occur in molecules which have permanent electric dipoles, right? Such as NH3 or H2. So a polar molecule has separate centers of positive and negative charges, and the ends of the dipole possesses positive charge, right? And these positive charges are denoted by the Greek word delta. The partial charges are always less than the unit electronic charge, that is 1.6 into 10 raised to power minus 19 coulomb. And these forces arises due to the interaction between positively charged ends of the polar molecules. The positive end of one molecule attracts the negative end of the other molecule and vice versa, right? So greater the dipole moment of the molecule, greater are the forces of attraction, right? And this effect was first studied by Kisam in 1912 and is also referred to as orientation effect. And these forces are also called as Kisam forces, and these forces produce a net attractive effect, right? So let us write this down. So first point is these types of forces occur in molecules which have permanent electric dipoles HCl, NH3, H2, right, etc. The second point would be a polar molecule separate centers of positive and negative charges, and the ends of the dipoles possesses partial charges, right? These charges are shown by Greek letter delta, and these partial charges are always less than the unit electronic charge, 1.6 10 raised to power minus 19 coulombs, right? And these forces arises due to these forces arises due to interaction between oppositely charged ends of the polar molecule, right? The positive end of one molecule attracts the negative end of the other, right? And vice versa. So for example, let me drag a picture. Here we see that the dipole-dipole. So this figure shows the dipole-dipole interaction between the hydrogen chloride molecules, right? So this is a hydrogen chloride molecule. So this is a delta positive charge, and this is delta negative charge, right? So more charge density towards the chlorine, and when this molecule one interacts with other molecule, what we see is this negatively charged delta charge attracts the positive charge of hydrogen, and this gives the dipole-dipole interaction between two HCl molecules, right? For example, the next slide, right? Greater the dipole moment of the molecule, greater are the forces of attraction, right? Greater the dipole moment, greater are the forces of attraction, right? And this effect was first studied by Kisam, right, in 1912, and is also referred to as orientation effect. And these forces are also called as, you guessed it right, Kisam forces are also called as, right? So the interactions are stronger than so these interactions are stronger than London forces. However, these are weaker than the ion-ion interaction because only partial charges are involved. The interaction decreases with increase in the distance between the dipoles. As in London forces, the interaction energy is inversely proportional to the distance between the polar molecule. And dipole-dipole interaction energy between stationary polar molecule, right, as in solids, is proportional to 1 by r cube. And that between the rotating polar molecules is proportional to 1 by r to the power 6, where r is the distance between the polar molecules, right? It may be noted that besides dipole-dipole interaction, polar molecules can interact by London forces also. As a result, the cumulative effect is that the total intermolecular forces in the polar molecule increases, right? So what we have is these interactions are stronger than London forces, right? Next point, however, just move on to the next page. However, these are weaker than these interactions are weaker than ion-ion interaction because only partial charges are involved. The interaction decreases with increase in the distance between the dipole molecules, right? With increase of distance between the dipole. Right? So as in London forces, the interaction energy is inversely proportional to the distance between the polar molecules, right? And dipole-dipole interactions, energy between stationary polar molecule as in solid is proportional to the 1 by r cube, and that between rotating polar molecule is proportional to 1 by r to the power 6, where r is the distance between polar molecules. Right? It may be noted that besides dipole-dipole interactions, polar molecules can interact by London forces also. Hence, as a result, community effect is that total intermolecular forces in polar molecule increases. So the next topic which we are going to study is dipole-induced dipole forces. These types of attractive forces operate between the polar molecules having permanent dipole and the molecules having not permanent dipole. For example, if a molecule of a substance are non-polar, such as noble gases, they do not possess any dipole. However, when these molecules come in the neighborhood of other molecules, which are permanent dipole, an induced dipole appears on this non-polar molecule. This is because the electron cloud of non-polar atom or molecule gets deformed due to the electric field of the polar molecule. This causes a shift in the center of gravity of the negative charges relative to the nuclear charge, and this results in the formation of an induced dipole moment. As the size of the atom or molecule increases, the influence of the electric dipole on it also increases, and the interaction energy is also proportional to the 1 by r to the power 6 and depends on the dipole moment of the polar molecule and polarizability of the non-polar atom or molecule. Molecules or atoms of larger sizes have more tendency to get polarized. The forces existing between dipole and induced dipole are called as dipole-induced dipole forces, and the easier the molecules are deformed, that is easily polarizable, the greater the attractive forces. And this effect was studied by Debye in 1920 and are also known as induction effect. In this case also the cumulative effect of dispersion forces and dipole-dipole force and dipole-induced dipole interactions exist. The above three types of forces are collectively known as van der Waals forces, and the magnitude of each type of interaction will vary depending upon the type of the molecule. Right? So let us write this down. So these types of attractive forces operate between the polar molecules having permanent dipole and the molecules having no permanent dipole. For example, if the molecule of a substance are non-polar, they do not possess any dipole, right? However, when these molecules come into the neighborhood of other molecule which have permanent dipole, and induced dipole appears on this non-polar molecule. Right? This is because the electron cloud of the non-polar molecule, that is the non-polar molecule gets deformed due to the electric field of the polar molecule, right? This causes a shift in the center of gravity of the negative charge. This causes a shift in the center of gravity of the negative charge relative to the nuclear charge, and results in the formation of an induced dipole movement. As the size of the atom or molecule increases, the influence of the electric dipole on it also increases. The interaction energy proportional to 1 by r to the power 6. This depends upon the dipole moment of the polar molecule and polarizability of the non-polar atom or molecule. Molecules or atoms having larger size have more tendency to get polarized. And the forces existing between dipole and induced dipole are called as induced dipole forces, right? Existing between dipole and induced dipole are called as dipole induced dipole forces, right? The easier the molecules are deformed, that is easy polarizability, the greater are the attractive force. The easier the molecules are deformed, the greater are the attractive force, right? This effect was studied by Debye in 1920 and is known as induction effect. In this case also, cumulative effect of dispersion forces and dipole-induced dipole interaction exists. See, the dispersion. So when we combine all these forces, which are dispersion or London forces plus dipole-dipole forces plus dipole-induced dipole forces, we add together, we get what are called as van der Waals forces, right? The magnitude of each interaction will vary depending on the type of molecule. The magnitude of each type of interaction will vary depending upon the type of the molecule. The next force which we are going to study, next and last, is hydrogen bond. So hydrogen bond is a special case of dipole-dipole interaction when hydrogen atom is bound to atoms of highly electronegative elements such as fluorine, oxygen, or nitrogen. The hydrogen atom forms a weak bond with the electronegative atom of the other molecule. This weak bond is called hydrogen bond. For example, in hydrogen fluoride, the hydrogen atom forms a weak bond with the fluorine atom of the neighboring molecule, while remaining bonded to its fluorine atom. In other words, hydrogen atom acts as a bridge between two atoms, holding one atom by a covalent bond and the other by a hydrogen bond. The hydrogen bond is represented with a dashed line, while the covalent bond is represented by a solid line. As a result of hydrogen bonding, HF exists as a cluster of hydrogen fluoride molecule, and it may be noted that although hydrogen bonding is regarded as being limited to nitrogen, oxygen, and fluorine, but some molecule containing chlorine may also participate in hydrogen bonding. The energy of hydrogen bond varies between 10 to 100 kilojoule per mole. This is quite a significant amount of energy, and therefore hydrogen bonds are powerful forces in determining the properties of many compounds. These play significant role in proteins and nucleic acid. The strength of hydrogen bond is determined by the Coulombic interaction between the lone pair of electrons of the electronegative atom of one molecule and hydrogen atom of the other molecule. Okay, so let us write this down. Hydrogen bond. Hydrogen bond is a special case of dipole-dipole interaction when hydrogen atom is bonded to atoms of highly electronegative elements such as fluorine, oxygen, or nitrogen. The hydrogen atom forms a weak bond with electronegative atom of the other molecule. This weak bond is called as hydrogen bond. For example, in hydrogen fluoride, HF, hydrogen bond forms a weak bond with fluorine atom of the neighboring molecule while remaining bonded to its fluorine atoms. This may be shown as following. Hydrogen is bonded to fluorine, which is bonded to by a hydrogen bond. Hydrogen is again bonded to fluorine, again hydrogen bond, fluorine. This goes on continuous. So this is delta positive charge, delta negative, delta positive, delta negative, so on and so forth. Right? So in other words, hydrogen atom acts as a bridge between two atoms, holding one atom by a covalent bond and other atom by hydrogen bond. The hydrogen bond is represented by dashed line, whereas covalent bond is represented by solid line. Right? As a result of hydrogen bonding, HF exists as a cluster of hydrogen fluoride molecule, as a cluster of hydrogen fluoride molecule, and is represented by HF to the power n. Right? It may be noted that although hydrogen bonding is regarded as being limited to nitrogen, oxygen, and fluorine, but some molecules containing fluorine may also show hydrogen bonding. Okay? Next point is the energy of hydrogen bond varies between 10 to 100 kilojoule per mole. This is quite a significant amount of energy, right? The strength of hydrogen bond is determined by the Coulombic interaction between the lone pair of electrons of the electronegative atom of one molecule and hydrogen atom of the other molecule. So in the intermolecular forces discussed so far are all attractive forces, right? The intermolecular forces which we have discussed so far are all attractive forces. However, molecule also exert repulsive forces on one another. When two molecules are brought into close contact with each other, the repulsive forces may also start operating. These are between electron clouds and between the nuclei of two molecules. And the magnitude of repulsive forces increases rapidly as the distance between the molecule increases. This is the reason that liquids and solids are hard to compress. Are hard to compress. In liquids and solids, the molecules are already close and therefore they resist further compression because that would result in increase of repulsion force. Right? So let us also write this down. So intermolecular forces, which we have discussed till now so far, are all attractive forces. However, molecules also exert repulsive forces on one another. When two molecules are brought into close contact with each other, when two molecules are brought into close contact with each other, the repulsive forces may also start operating. These are between the electron clouds and between the nuclei of two molecules. This is the reason that liquids and solids, the magnitude of repulsive forces, magnitude of repulsive increases rapidly as the distance between the molecule decreases. In liquids and solids, the molecules are already close and therefore they resist further compression because that would result in the increase of repulsive interaction. So in summary, what we have seen today, we have seen three other types of interactions. These are dipole-dipole interaction. Then we have seen dipole-induced dipole forces. The third is hydrogen bonding. We have also seen that these forces are all attractive in nature, and at the intermolecular level, there also exist repulsive forces. And because of these repulsive forces, both the liquids and solids are hard to compress because in liquids and solids, the molecules are already close and therefore they resist further compression because that would result in increase of repulsive force, repulsive interactions. Right? So in the next class, what we are going to study, we are going to study the general characteristics of gases and types of bonding and melting and points. Further, we also study about the various types of measurement. What are the unit of atmospheric pressure, measurement of mass, what are different manometers and all. So I thank you all for attending this class, and I hope to see you all again in the next class. Thank you.